In this video, we will be talking about a topic in AI which is called PAC learning or probably approximately correct learning. So coming to the background, so PAC learning model was introduced by LG Valiant back in 1984 in a paper called Computational Learning Theory. It is a framework for mathematical analysis of machine learning. So the model is fed with samples to construct a generalization function that can make predictions on new data. PAC learning is useful in settings where only approximately correct answers is required and we do not care about exact representation of the original function. So coming to the intuition of PAC, the PAC model belongs to a class of learning models which is characterized by learning from examples. Let's say if f is a target function that the model needs to learn when random variables are provided, the samples are in the form of x and fx, where x is binary representation of the input features and fx is the target variable which we need to predict, which is again in the Boolean, which takes Boolean values. So based on these examples, the learner must be able to predict the target function, which is f mapped from 0, 1 in n-dimensional space to 0, 1, which is the target space. Since the model is approximate, we need to put certain relaxations in the model so that the model can come up with approximate solutions. So we may allow a small probability that the learning algorithm fails. This would be in some kind of worst cases where examples that are picked up from the distribution and are provided to learner don't contain much information to help the target function. Generally, these are the outliers which do not add any value to the model. We may spare the learner from learning the exact concept. If the learner can find a function h which approximates a function f, it is still fine. So it can be shown from the diagram that suppose if we have a teacher and a learner, then a set of labeled examples are passed to the learner and the learner learns those examples with high degree of approximation. But it is not necessary that it will be able to predict all the labels correctly every time. So the above two factors that we use to explain the relaxations are quantified as epsilon and delta. The epsilon gives an upper bound on the error with which the h is predicted. The upper bound on which the h approximates a function f. And delta gives the probability of failing in achieving this accuracy. So the error with which h approximates f is quantified as error of hf is equal to probability where hx is not equal to fx. That is those values, those samples for which the target variables differ. So diagrammatically, it can be represented, the error can be represented as follows, where hf is the approximate function and f is the true function. The shaded region shows the mislabeled values, whereas the overlapping region shows the correct prediction. Now coming to the formal definition of PAC learnability. So consider a concept class C defined over a set of instances x of length n and learner L using hypothesis space capital H. Then C is PAC learnable by L using H if for all C belonging to the concept class C, distribution D over X such that epsilon and delta are the errors, then the learner L will with probability at least 1 minus delta output a hypothesis H belonging to hypothesis space S H such that the error D on the distribution D is less than epsilon. So the probability of with which So the minimum number of samples required for the model to train is given by m greater than log of h plus log of 1 by delta whole divided by epsilon, where h is the size of hypothesis space and delta is the confidence and epsilon is the upper bound on the error.
I will be discussing about VC dimensions and shattering. A configuration of endpoints on the plane is any placement of endpoints. We basically place these endpoints in any positions, and this is called a configuration of. In order to have a VC dimension of at least n, a classifier must be able to shatter a single configuration of endpoint. So any of these configuration of endpoints you take, a classifier must be able, any single configuration will take, and the classifier must be able to shatter this configuration. Now what is called shattering? In order to shatter a configuration of points, the classifier must be basically able to, for every possible assignment. So for n points, if we take two states, positive and negative, there will basically be 2 raised to the power n states for a single configuration. So if the classifier is able to partition the plane such that the positive points are separated from the negative point, we basically say that the classifier has shattered the configuration. For configuration of endpoints, there are 2 raised to the power n possible assignments of positive or negative. So the classifier must be able to properly separate the points in each of these assignments. I've taken an example. Here we show that the VC dimension for a linear classifier is at least 3, since it is able to shatter this configuration of 3 points. In each, we'll have a look that in each 2 raised to the power 3, that is 8 possible assignments of positive negative, the classifier is distinctly able to separate the two classes. So for the first image, all are negative, and the arrow means that it's pointing to the positive side. So we have taken a configuration, a single configuration of endpoints, and we have plotted all the 8 states for that configuration. So for the first one, it's able to all the positive are on one side, negative. So similarly for all the 8 states, it's able to classify. So what are the applications of this VC dimension? It is important to understand the practical implications of VC dimension. In most of the cases, the exact VC dimension of a classifier is not so important. It is rather used more so to classify different types of algorithms by their complexity. For example, the class of simple classifiers could include basic shapes like lines, circles, or rectangles. So we basically have a classifier shaped like a 2D classifier shaped like lines, circles, and rectangles, which separate the boundary between positive and negative assignment. So, whereas a class of complex classifiers could include classifiers such as multi-layer perceptrons, boosted trees, or other non-linear classifiers. These are non-linear. The complexity of a classification algorithm is directly related to its VC dimension. It is related to trade-off between bias and variance. So let us see this one. At some level of model complexity, there will exist an ideal balance between bias and variance, denoted by dotted vertical line, at which you're neither underfitting nor overfitting your data. In other words, you should aim to choose a classifier with a level of complexity that is just enough for your classification. Any less would lead to underfitting and any more would lead to overfitting. So, in the above image, we visualize the effects of model complexity. On the bottom, each SI represents a set of models that are similar in VC dimension or complexity. On the graph, VC dimension is measured on the x-axis as h. We observe that as complexity increases, we transition from underfitting to overfitting. Adding complexity is good until a certain point, after which we begin to overfit on the print.
Agnostic learner. In agnostic learning, we assume that there is no existence of concept which labels our instances. Whereas in non-agnostic learning, we assumed that there is a concept which correctly labels each instances of X to some Y. What are the real life scenarios where it can occur? Such as in social media post classification, if it is a hateful post or it is a appropriate post. In such cases, there might not be an exact answer if it is appropriate or inappropriate. In such cases, it is very difficult to assume, basically impossible to assume a concept which can accurately classify. So these type of scenarios create a space for agnostic learning. Notations. In agnostic learning, we assume a distribution D where x cross y instead of x and then choosing a concept. We are basically choosing a joint probability distribution over x cross y. Now, this D has the possibility that there is a case of xy that belongs to D and xy dash that belongs to D and y not equal to y dash. That is basically that both x are same but their target values, that is y, can be different in this case. Like the example we discussed about social media post, that the post can be appropriate for some concepts and for some concepts it will be very ambiguous to describe it as appropriate. So it is possible that it can be appropriate and inappropriate at both uh, that that condition basically breaks the definition of function, so it is impossible to assume a relevant concept. Now, picking x comma y is basically picking x from x and then y from y. Thus we define marginal distribution of d with respect to p or x, which is basically integrating p or x comma y, that is the joint distribution of x and y, with y equal to y and y varying to all space of y. Now, the joint distribution which we have assumed p r of x and y can be written as the product of probability distribution of d with respect to x into conditional label distribution, that is p r y by x. Now, here in this case, the error will be defined as the mean of instances where our prediction function h prediction x h does not give y, which is in our joint distribution. The algorithm can be written as follows. It is also learning without realizability, which is basically non-agnostic methods. So we define PT distribution tasks and define some step size hyperparameters basically which define. Then we define randomly sliced theta parameters, and then we take a batch of tasks from PT, and then we calculate our loss with respect to our model. Then we calculate the gradient of that loss, and then we update parameters using our hyperparameters alpha and beta alpha, and then finally we update the theta with beta. Here alpha and beta can be understood as a learning rate for our function parameters theta and theta dash.